This is a very short chapter, and so today we're going to be doing objective 1 and 4. So both of them are just applications of integration, and so this whole chapter kind of involves all of that idea. So the very first component that we have to take a look at is we are trying to find the area of the region between two curves. So up to now, we have only found the area under the curve and or between a curve and the x-axis. So we would be just given, one function, and our area would be bounded also by the x-axis. And so that's what we've done so far. And that would just be the integral from a to b of whatever our function was. And so we're just going to expand upon that just a little bit. So if we have two functions that are continuous, and in this particular definition, we'll just say g of x is our lower function, and it may intersect f of x, but it will be below it. And that would be for all values of x from a to b. Then the area of the region bounded by the graphs of f and g, and then the vertical lines, x equals a and x equals b, those are our limits. Then that function would be given as the integral from a to b of f of x minus g of x. So what that is, so that kind of is like a formula, so to speak. But what we're taking a look at is, so here is my function f of x. So if I were to find the area of just f of x, right, it would be this section here. So it would be the area bounded by f of x down to the x-axis, right? So that would be just that integral itself, right? So that would be the integral from a to b, or hold on, there we go. So the integral from a to b of f of x dx, and that would be that section in red, right? So if I don't want that section below it, which is bounded by g of x, so if I take a look at the section of g of x, that would be this piece right here, right? Because there's g of x. Yowza, get my thumb off of the button. There we go. Okay, so that area of g of x, right? So that would be the integral from a to b of g of x dx. That would be the area shaded in blue. But the section that I'm actually looking for is that piece in between, right? And so this is the piece I'm looking for. So the area in red is too big, right? And it's too big by the area in blue. And so I would just find the difference between them. And then I know if I have similar limits, then I can just look at that function as the integral from a to b of just f of x minus g of x, and then with respect to x. So that's all we're doing, right? We're just finding the integral of, what we call the upper function, and then we're going to subtract from it the function that's below that, because they both are bounded by that x-axis as well. And so that is what we're going to be doing. And we're just going to go ahead and write it just as one integral, even though what is actually happening is we're finding the area under one function and then subtracting the area under the other function. Okay? All right, so let's go ahead and take a look at an example here. So for this one, what we're looking to do is we want to find the area between f of x equals x squared plus 2, so a parabola, and then g of x equals negative x minus 1 on the integral from 1 to 2. So the first thing we want to do is we want to graph the given functions, and you can either, if you happen to know your parent functions pretty well, just do it by hand. Otherwise, pull out your graphing calculator or Desmos, but you always want to have a picture of what it is that we're working with, okay? All right, so I'm just going to set up, and I don't need a lot of room for the math. So I'm just going to take up a fair amount of space to make my graph. So x squared plus 2, so I know my functions pretty well, so I can do this one by hand. So I know that this is a quadratic shifted up 2 units. So I'm just going to go up 2 units, and then I'm going to draw in my quadratic. Beautiful function there, and I'll call that f of x. And then now I'm going to go ahead and graph in g of x, and then I'm just going to use a different color here. So for g of x, so I know this is a line that has a slope of -1 and a y-intercept of -1. So I'm going to go down to -1, and then with a slope of -1, so I'm going to go down 1 over 1, and then I didn't, draw in my x-axis scale. So let me just do that, okay? And so then that would be g of x. And then I'm bounded by 1 and 2, right? So my limits are from 1 and 2. So there's 1, and then I'll just say 2 is over here. And so I know I'm looking at the section from 1 to 2. So this is the area that I'm trying to find, okay? So I graph the given functions, and then the limits I didn't have to determine, they were just given, right? So that was given by this interval. Sometimes they're not, and they'll be intersection points, and then we'll have to find them. And then I shaded the area that I'm searching for, and then I want to draw a segment, and this is just to kind of help prep us for the future objective here. So I want to draw a segment that will represent the height of the shaded region. So again, this isn't necessarily something I have to do for area, but it is to help me with the next section. So the height, so if I take a look from the top of my function to the bottom of my function, so that is the height of one particular rectangle. So remember, integration is Riemann sums, which are rectangles being added together. So that particular section. And so then now I want to find the height of that particular section in terms of x. So no matter where I am on this graph, right? So, if I drew it over here, the top of that rectangle is defined by f of x, the bottom by g of x. If my neighbor drew it over a little farther to the right, it doesn't matter. The top is defined by f of x, the bottom by g of x. So that height is a changing value, right? So it is a changing value. And so I know that it changes depending upon what my x value is. Okay, so that's why when we write out what is our height in terms of x, we know that it's going to vary. It's not going to be like 12 and 10 and 9. It's going to be always in terms of x. So we have to write out what that is. So I usually use h of x. You can use whatever you want. So I use h of x to represent the height in terms of a variable. So the height of this function, right, is the top of it is defined by f of x. So the top is defined by x squared plus 2. So if I were at x equals 1.5, I would figure out the height by replacing x with 1.5. And then the bottom of it is defined by g of x. And so if I want to find that distance, I subtract, right, by finding distance. So minus, where is the bottom defined? And it's defined by g of x, which is negative x minus 1. Okay? So when I determine what that height is of that shaded region, I look at what is the top function defined by. So my top function. And then I subtract what is the bottom function. And that will give me the total distance depending upon what x is, right? So if I knew this height was at 5 and this was down here at -2, that total distance would be 7, 5 minus -2. Or if maybe I was over here somewhere, so the height was now at 4 and then maybe at, -1.5, that total distance would be 5.5, 4 minus 1.5. 4 minus -1.5. And so, but we have to do it in terms of x's because it's going to change depending upon where we are. So how do I always find h of x? I do where is the top of that area defined by minus where is that bottom of that area defined by. So the top was defined by f of x, the bottom by g of x. And then because we're going to have to integrate, we are going to simplify always just a little bit. And that is only just to make that arithmetic a little bit easier or to type it into the calculator a little easier. So minus a negative is a positive and minus a -1 is a positive. And again, this is only to make it easier for me when I either have to integrate it by hand or if I have to type it into my calculator. That's why we're going to simplify. So now that I have h of x, then now I just set up my integral. So then I know the area of that shaded region will be the integral from 1 to 2, and I got that from my limits or from the left x to the right x of h of x. And then with respect to x. And then for this one here, or for this chapter in general, we are just going to be looking at setting up our functions and then using our calculators or Desmos to evaluate that integral. And so then I would just type that into my calculator or into Desmos, and it is actually an approximation because it is a decimal. So that would be 6.833, and I always want to go to 3 decimal places. So that area of that shaded region would be 6.833. Okay. All right, so let's go ahead and take a look at example 2. So my advice right now would be to press pause and then try to graph this on Desmos or in your graphing calculator and get a picture of this. Because this is probably not one that we would know easily without having to do some factoring and some fancy stuff. All right, so I'm going to go ahead and so I already have a second screen up with Desmos typed in. So I know that it's a cubic and it did something like this. This is not going to be to scale, but the best I got for you. So that is my cubic. So I'm going to use subscripts here. So Y1. And then my quadratic did something. Oh, that's awful. Okay. Work with me here, people. And then I'll call this one Y2. Okay, so it didn't even look anything like that, but we're going to say it's that. All right, so we want the area that is bounded by these two functions. So the only sections that are bounded are this one here and this one here. So if I look between these two sections, they're not completely bounded, right? It's an infinite area, so not bounded. If I look between these two right here, if I extended it out, again, this is not a bounded region, right? It goes out to infinity. So I actually have 2 different areas that I need to find independently from each other. So I'm going to call this one here area 1 and this one here area 2. All right, so if I look at this function, so let's start with area 1. So I'll just call this one area 1 right here. So I need to know my limits. So my limits were not given this time. We're expected to find them. So I know that it's going to be where it's bounded. So that would be at the intersection point. So one of the limits is 0. And then this one right here, I have to find. So if I'm on Desmos, I would just look at the intersection. Or if I'm on my graphing calculator, I would have my graphing calculator find it. And if you don't remember how to do that, be sure to ask. So that intersection point is at 1. And then I'm going to go ahead and do this one as well. And then that would be at 3. So if you didn't do that independently, you should try to find that yourself just to kind of refresh your memory. Okay, so for area 1, so I'm going to first find that height. So again, for the height, we want to look at from the top of the shaded region down to the bottom of the shaded region, right? So that is my h of x there. So where is the top of this region defined by? And it's defined by the cubic, right? So it's defined by the cubic. So that would be y1. So that would be x cubed minus 3x squared plus 3x. And then minus, where is the bottom of the function defined, right? So the bottom of the function is defined by the parabola, so minus y2, which was x squared, okay? And then I'm going to go ahead and just simplify that just a little bit. So that would be x cubed, and then negative 3x squared minus 1x squared is negative 4x squared, and then plus 3x. So there is area 1's height. And so then what would that area be then? So that area 1 would be equal to the integral of my h of x and then that's dx, and then that goes from 0 to 1, 0 to 1. And then again, I would either type that into my graphing calculator or I would type that into Desmos. And so for that particular one, I ended up with 0.4166. And I'm going to go out an extra decimal because I know that I want to be rounding out at least 1 extra decimal in the preliminary part of the problem so that my final answer is accurate to 3 decimals. All right, so this also would be a good time to press pause to find area 2 and then forward to see if you got the same thing I did. All right, so for area 2, so let's talk about that particular height. So when I go to look at that height, so I'm going to go from here to here. So the top of the function this time is defined by the quadratic, right? Because it's switched locations. So that top function is defined by x squared, and then minus, and then the bottom function is defined by the cubic. So that would be x cubed minus 3x squared plus 3x. And then let's go ahead and distribute in that negative. And I can combine like terms. So I would have, and I'm going to put this in descending order. So I would have negative x cubed and then plus 4x squared and then minus 3x. Right. Yeah. Okay. So then once I get to there, so then area 2 would be the integral from 1 to 3 of the y2 minus the y1. So that would be this h of x here. And then for this one, I ended up with 2.667. Okay. All right. So then my total area would be those combined values. And so I have 3.083. And then always, of course, you can round or truncate. So let's keep that in mind as well. So I think I truncated on one and rounded on the other. But anyway, that would be my total area for that particular function. So just like a little tip here, if you ever got any of these to be negative, something's wrong because your area is what you're always finding. And so you should not be getting a negative value. So if you got something negative, then something is wrong, right? Because we are finding area, not anything that is directional. The most common mistake that people make on these problems, so if they get a negative answer, is they just have their heights flip-flopped. So they just did like the bottom function minus the top function. And that usually just means you would get the negative version of my answer. Don't just then force it positive. Go back and make that correction so that you have the top function minus the bottom function. Okay? So that's it for objective 1. So let's go ahead and we're going to take a look at objective 4 as well. So this is another application of integration, which, so it's kind of cool to see, where we're working with, like how does this apply to things? And so area, of course, being one of them, but arc length. So this is another idea. So arc length. And so we actually study arc length again in a later chapter. So this is when we get into our parametrics. So this is just kind of our beginning reference. So we'll review this arc length when we get into our parametric section as well, because we'll use the same formula. So what arc length is doing is if we have a curve, whatever your function might look like. So we'll just say that's our beautiful function there. And we want to know, like, how long is that curve from A, to B, if we want to figure out how long that is. So if we want to know the length of that particular section from A to B, we could certainly approximate it, right? We have that ability. And so now what we're trying to do is figure out, well, okay, I don't want to approximate it. I want to know exactly what it is. So how we do it is we use Pythagorean, right? So the distance between 2 points, right, wherever those 2 points are, like if I want to know how long that section is, then I would just do, Pythagorean theorem. I would find the horizontal distance, the vertical distance, and then I would find C. So I would do A squared plus B squared is equal to C squared, or the root of that, right? And so, which by the way, just to make sure we know that we cannot square root separately, so that doesn't equal A plus B. And that will give me that distance. And so that's really what we're doing here is we are finding, this is a Pythagorean theorem right here. The difference here though is that we have the square root of 1, which is really dx over dx is what we're doing here, squared, plus, and then dy over dx squared. So the change of x squared with respect to itself, and then the change of y squared with respect to x squared. And so that is what we're looking at, and that's how we're doing it. So we're taking these tiny little sections here, and then imagining like there's a little triangle. And so what is that dy dx compared to dx dx squared to get the distance here? And then like another like little section, a little triangle, and so on and so forth. And so we're finding these really teeny weeny lengths here, and then we are summing them, because that's what integration is doing, is summing up things. And so in this case, we are summing up little tiny distances on the triangle, right? The hypotenuse there. Okay, so that's just kind of some theoretical business. And if all of that just went, over the head, or it's just too hard to comprehend by me just yammering on, that is okay. The biggest thing then that you need to make sure you get is that this is a formula, and you need, oh, that is not highlighter, people. Okay, how about that? That's highlighter. So the number one thing, so if nothing I just said made sense, or it was just too hard to follow because it's just me going wah, 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 is I need to know that formula. So even if I have no idea what I just said, that is okay. We all know how to use a formula. So here we go. Example 1, find the arc length. How am I going to do that? I'm going to use that formula. So we're going from 1 to 8. So that means we use S for arc length. So we're going to integrate from 1 to 8. And then I'm following the formula, square root of 1 plus, and then they want me to take the derivative. So I will just do that off to the side here. So y prime, so take that derivative. So 2/3 times 3/2 is 1, and then reduce the power by 1. And then with the derivative, they want me to square it. So then I'm going to take that derivative, and then I'm going to square it, and then with respect to x. Again, my advice here would be to simplify a little bit before we put that into our calculator. So I am going to do 1 plus, and then I'm going to multiply -1/3 times 2. Again, just to make it easier to type into my calculator. And then from there, either use Desmos or your calculator, type it in, get an answer. And so I got 8.351 or 352 if you rounded. And that's it. All right. And then I don't think we need a second example for that.